Hello and welcome to this session. In this session, we are going to discuss partial derivatives, how to compute partial derivatives, and we will also discuss how to find derivatives using chain rule and higher order partial derivatives. In differentiation, we have discussed how to find derivative of a function of the form y equal to fx, where we have only one independent variable x. Now suppose we have a function of the form z is equal to f of xy, where we have two independent variables x and y and one dependent variable z. Now we want to find the rate of change of a function with respect to one of its variables. For this, we use partial differentiation and the result is referred to as partial derivative of the function with respect to the chosen independent variable. The symbol for partial derivative is del, or we can call it curly. Now let us discuss the method of finding partial derivative. Suppose we have a function z is equal to f of xy, where z is the dependent variable and x and y are independent variables. To find the partial derivative of z with respect to independent variable x, we will differentiate the given function with respect to x, treating the other independent variable y as constant. We denote this derivative by del z by del x, or curly z by curly x, or f sub x, or f sub x of xy, or del by del x of f of xy. That is partial derivative of f of xy with respect to x. Similarly, to find the partial derivative of the function z with respect to the independent variable y, we differentiate the given function with respect to y, treating the other independent variable x as constant. This is denoted by del z by del y, or f sub y, or f sub y of xy, or del by del y of f of xy. that is partial derivative of f of xy with respect to y. To make it more clear, let us consider an example. Suppose we have z is equal to 3x cube minus x square y square plus 2y. Here z is the dependent variable and x and y are independent variables. We first find the partial derivative of z with respect to x. For this, we differentiate z with respect to x, keeping y as constant. The partial derivative of z with respect to x is equal to 3 into 3x raised to power 3 minus 1, as the partial derivative of x raised to power 3 is 3x raised to power 3 minus 1 minus, as y is constant, so y square is also constant. So we only differentiate x square and we get 2x raised to power 2 minus 1 into y square plus, as y is constant, so its derivative will be 0. So plus 0. Hence partial derivative of z with respect to x will be equal to 9x square minus 2x y square. Similarly, we can differentiate z partially with respect to y, treating x as constant. We get partial derivative of z with respect to y equal to 0 minus x square into 2y plus 2 into 1, as x is constant. So partial derivative of z with respect to y will be equal to minus 2x square y plus 2. Now suppose we want to find its partial derivatives at the point 2, 3. We have del z by del x is equal to 9x square minus 2xy square, and del z by del y is equal to minus 2x square y plus 2. So here we write del z by del x at the point 2, 3 is equal to 9 into 2 square minus 2 into 2 into 3 square, which is equal to 36 minus 36, which is equal to 0. And del z by del y at the point 2, 3 will be equal to minus 2 into 2 square into 3 plus 2, which is equal to minus 24 plus 2, which is equal to minus 22. Here we put the value of x equal to 2 and y equal to 3 in the equations of partial derivatives with respect to x and y. Let us now discuss chain rule. Chain rule is applied when we have z as a function of two variables x and y, that is, z is equal to f of xy, where x and y are further functions of one or more independent variables. Let us first see the chain rule for the function z equal to f of xy, where x and y are functions in one independent variable. So here let z be equal to f of xy. Also x is equal to g of t and y is equal to h of t, where f, g and h are differentiable. That is, z is a function of x and y, and further x and y are functions of independent variable t. Then z is a differentiable function of t. That means the derivative of z with respect to t, that is dz by dt, will be equal to del z by del x into dx by dt plus del z by del y into dy by dt. See that x and y are functions in only one independent variable t. That is why we have used total differential instead of partial differential. Let us see the chain rule when variables x and y are further functions of two independent variables. Let z be equal to f of xy. Also, x is equal to g of st and y is equal to h of st, where f, g and h are differentiable. So here we have z is a function of x and y, and further x and y are functions of s and t. So we find the partial derivative of z with respect to s and the partial derivative of z with respect to t. Using del z by del s is equal to del z by del x into del x by del s plus del z by del y into del y by del s, and del z by del t is equal to del z by del x into del x by del t plus del z by del y into del y by del t. Let us consider an example. Let z be equal to x square plus 2y and x is equal to t square, y is equal to 2t. Here we can apply chain rule for one independent variable, that is dz by dt is equal to del z by del x into dx by dt plus del z by del y into dy by dt. Now del z by del x is equal to 2x plus 0, as we are partially differentiating z with respect to x, keeping y as constant. Dx by dt is equal to 2t. Del z by del y, that is partial derivative of z with respect to y, will be equal to 0 as x is constant, plus 2 into 1 as the derivative of y is 1, and dy by dt is equal to 2. This implies dz by dt is equal to 2x into 2t plus 2 into 2, that is equal to 4xt plus 4. Now we eliminate x by using the equation x is equal to t square, and we get dz by dt is equal to 4 into t square into t plus 4, which is equal to 4 into t cube plus 1. Now let us discuss implicit differentiation. If the equation f of x, y, z equal to 0 defines z implicitly as a differentiable function of x and y, then the partial derivative of z with respect to x will be equal to minus of f sub x of xyz upon f sub z of xyz, and partial derivative of z with respect to y is equal to minus of f sub y of xyz upon f sub z of xyz, where f sub z of xyz is not equal to 0. For example, we have xyz plus x square plus yz square equal to 0. This is an implicit function. We have to find del z by del x. First we differentiate this function with respect to x, treating y and z as constant. We get f sub x of xyz equal to yz plus 2x. Now we differentiate with respect to z, keeping x and y constant. We get f sub z of xyz will be equal to xy plus 2yz. So, del z by del x is equal to minus of f sub x of xyz upon f sub z of xyz equal to minus of yz plus 2x upon xy plus 2yz. Now let us discuss higher order partial derivatives. Let z be equal to f of xy, where f is differentiable function if we differentiate it with respect to x twice, we write del by del x of del f by del x is equal to del square f by del x square, which can also be written as f sub double x. Similarly, if we differentiate it with respect to y twice, we write del by del y of del f by del y is equal to del square f by del y square, which can also be written as f sub of double y. Now if we differentiate first with respect to x and then with respect to y, we write del by del y of del f by del x will be equal to del square f by del y del x, which can also be written as f sub of xy. Similarly, if we differentiate first with respect to y and then with respect to x, we write del by del x of del f by del y, which is equal to del square f by del x del y. That can be written as f sub of yx. Let us consider an example where z is equal to 3x cube minus x square y square plus 2y. We discussed this example earlier and we found that the partial derivative of z with respect to x, that is del z by del x, is equal to 9x square minus 2xy square. Let us again differentiate this with respect to x, treating y as constant. We get del square f by del x square is equal to 18x minus 2y square. Now suppose here we want to find f sub of xy, that is, we first find f sub x, which is equal to 9x square minus 2xy square. Now we differentiate this with respect to y, treating x as constant. We get f sub xy is equal to 0 minus 4xy. Therefore, f sub xy is equal to minus 4xy, which is the required partial derivative. Thus, in this session, we have discussed partial derivatives, chain rule, and higher order partial derivatives. This completes our session. Hope you enjoyed this session.